Okay, so I think we can get started. So I will make it extremely brief. So let's welcome Farzan Vafa from the Center of Mathematical Science and Applications, Harvard. We'll talk about liquid crystals, topological defects, and morphogenesis.
Great. Thank you. Start by thanking the Quantitative for organizing this conference this past few weeks. They have a lot of next week, and also thank you for giving the opportunity to present recent work on liquid crystals, topological defects, and morphogenesis. And this is based on works with Grace and David Nelson at Harvard, as well as with Mahadevan at Harvard. So this will be kind of based in two parts. In the first part, we're going to set up and then the second part, we're going to allow this surface to be dynamical, to change, and we're going to see that we can get growth. And this part's based primarily on the work with Mahadevan. So I send these talks and also feel free to just interrupt and whenever discussion. So welcome questions. Okay, let's warm up with this. Find the ground a sphere. So there's some math theorems that tell us that there has to be topological defects of this vector field, and there has to be the net charge is +2, and there has to be at least two of them. And if you think about topological defects as charges, then they're going to want to repel each other, be as far away from each other as possible. So they're going to be on the north and south poles, for example. And now, so this is the p equals 1, this because it's one pole, rotational symmetry comes to itself. So now let's suppose that let's zoom in and look near the north pole. And instead of looking at a vector, let's a double-headed, what's known as a nematic or a line field. So here we lose this 2-pi rotational symmetry because if it just by rotation by pi gets to itself. Then in this case, because of the allowed configuration to rotate by pi, then the quantum of charge is changed from plus in units of 1 to units of 1/2. So this +1 is going to split into 2 + 1/2 because again these defects are charges that kind of want. And so that's what happens here. And now we might ask what happens in the case of a sphere. And in this case, you get a baseball type. I don't know, 150 plus years ago, and somehow this, if you look at this baseball, there's these stitches, and this looks like maybe the nematogens. And so then there's going to be 4 + 1/2 defects, and these are going to be situated at the vertices of a tetrahedron, because this is essentially if they want to repel each other, how it goes. So there's many examples of Keyfold symmetric liquid crystals. Like first example is there's just many. First example of motivation is if you look at the double emulsion nematic shells, then depending on the thickness of the shells, you could have different types of defect configurations depending on that. And this is a nematic. Another example, which is non-nematic or polar, is the epithelium of a developing shrimp. So then the cells that are dividing, and as the cells divide, they're going to establish and then maintain this fourfold or the quadratic order. So this looks like square and.
So what's labeled in there? So what are we seeing there in that image on the top right?
Top right. This one?
Yep.
Cells.
They have triangle symmetry, is it? Or what a Balkan symmetry? That's what it is.
Yeah, because this looks like the form J-curve.
Yeah.
So each of these is a cell, and then they just, which is really remarkable that we see, because normally cells are like hexagonal-ish shape, but this is like pretty. Yeah, so this was in the, I forgot to say, so the first one, this was in the France, this was in David Waite's group at Harvard, this is in Sebastian Strikens at Santa Barbara. And then it's really remarkable, haven't seen other examples of this in biology. And then the last example in the starfish embryos, we also had like
At the risk of beating a dead horse, I mean, this is just a local hexsymmetry. You use the word hexatic here in the formal hexatic quasi-language all the way or not?
oh, I just mean that by just mean rotational doesn't have to.
That's all right, at least at the same length scale.
Not a long range, right?
Yeah.
So locally, right?
Yes, locally.
Yeah, and it's,
So I mean, I guess the point is you are invoking a Emil Wagner here.
Sure, yeah, but there's just some examples of motivations.
So how big? Maybe I should ask Alex. How big do these things get?
Maybe, well, 5-6 times this, because it's not microscopically
Yeah.
large. We have not, so I know hexatic, there's sort of sometimes a bit because it's hexagonal order that we can classify, but we have no idea about now in transitions or anything this direction. So there's no way to make it.
and then when you put more than like a hex crystal,
So yeah,
crystal or something,
I
yeah.
don't- yeah, it's
Crystal art.
crystal with hexagonal order,
Yeah.
so locally for sure.
Well, this topological similar, each of these objects is an embryo, right?
This is an embryo, yeah.
So it's gazillion embryos, right?
Yes.
Yeah, but yeah, this is in the group by MIT this. And then so alluded to, but so we saw this in the case of a sphere that it has partial defects and I asked like, are they actually important? Do they do anything? And it turns out that there's many examples recently where they do seem to play a role in biology. In particular, we're focusing on morphogenesis. So in this first example, in this MDCK cells, the equations of the plus half defect, the cells are this. So this governs cell death, which is important biological function, and the next one in the neuroprogenitor cells. And in this final example, what we're going to be later focusing on is that the twas, they are they seem to govern like where these they coincide with topological features. So we're going to see that the head, foot, tentacles seem to be locations, and but this is ultimately where we're going to be going towards. So in this talk, I'm really focusing on and today we have to define a coordinate system, and of course it doesn't change any of the physics that you choose, but some coordinate systems are much more convenient than others. So the one we're going to be using for this bond that's we're going to see is going to be convenient is called isothermal or conformal coordinates. Here is you're in 2 dimensions, so we're going to define a compass coordinate called z. We think about it as x plus I y. And then for a 2D curved surface, if for 2D we know there's this thanks to Gauss from 200 years ago, we could write the metric, the length element squared, ds squared, as e to the phi dz bar. For phi is going to be some real function of z and z bar that is. So and the e to the phi is known as the conformal factor. The reason being that in science, the magneticity and e to the phi represents how it has isotropic stretching at every single point. And then we're going to later see that we could really interpret this the phi as a geometric contribution to the potential. So we're going to like some physical meaning. So we're going to also is going to play the role of that potential in this context. So that's what we'll so in the back of mind, always keep in always think of remember like electrostatics. We're going to be constantly alluding to it. So that's about the geometry, but we're also in the examples do some of those like orientational orders. So how do we describe that on these curved surfaces? We're going to denote it by Q, liquid crystal with p-fold rotational symmetry. So examples that we saw are polar, which is P is 1, nematic P is 2, hexatic P is 6. And then in these coordinates, Q has only 2 non-zero components, which we're going to label Q, which is just the z to z, etc. component, P such indices, and Q bar, which is Q c bar, z bar, etc. component, which again, they're P such indices. And this intuitively kind of makes sense because if we're assuming that the orientational order lies completely within the tangent plane. We assume there's no orthogonal components or anything, so everything lies within. So if we want to describe orientational order, all we need is one is just one is the strength of the order. So that's 2 degrees of freedom. So then in these coordinates, we can capture it by a complex degree of freedom. So it's consistent, and because one would think that if you want to work, for example, in Cartesian coordinates, this would be very messy because like there's going to be strengths between them. But in these coordinates, it gets very simple.
How do you deal with inherent length scale in a lot of these systems? And the conformal which stretches things back and forth?
Person, what do you mean by the
Like,
Geometry, because you're talking about the order parameter on the, right? It's a different thing.
yeah, okay, I'll ask again in case. Keep going, yeah.
anything?
And so these the Z components, this is not a tensor-like or the tensor-like component, or this is just a notational
Oh, it's a,
vehicle basically to add the numbers of Z's, and this is.
oh, you know, Q. Real component. Assuming that and if you can show
So it's a similar spirit like the real values.
yeah,
Tensors where you have so
exactly.
many redundant
Exactly,
components.
yeah, exactly. It's just a generalization of what we know for the nematic, which is I mean 2 tensor products we have to take. So Q is this single value object, so it's going to be we don't have to deal with multi-valueness here.
So and what happened to topological defects?
Right, so I mean, so get this.
Okay.
I guess that's fine.
Yeah, exactly. So but presumably then you could have multi-value.
Yes.
It's
Okay.
clear and there can be. Yeah.
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 That'd be important. Okay, let's. Any other questions? Okay, so as an example, let's talk about the cone. It's gonna be a very useful example for us. So we all know what cones are, and so this is a cone, and it's gonna be, so in terms of that half angle beta, we're gonna define what we call an apex charge pi, defined to be 1 minus sine beta. Then we're gonna show that if we take the Gaussian curvature K and integrate it, and you just get 2 pi chi. And so we can think about chi as like to turn a disk into a cone, meaning one way to form a cone is you take a disk, you cut out a wedge, and then you glue the 2 boundaries together, and that's how you form a cone. So chi is simply the function that you is a cut out anything. So it's all. So we'll see that chi really, we can't do anything about it as a charge, even though I'm calling it charge for now, we'll justify it later. And explicitly for a cone in these coordinates, phi is just minus chi log zz bar. So it's a log, and we'll see this log is very useful, this form, as a teaser. So already see that because of the covariant derivatives of flux and the parallel transport, and because of the curvature, this becomes tricky. For example, if we take, let's say this identified boundary, we cut out theta, take this vector, and we just make a point arrow, but since this boundary is at the boundary, they have to be exactly the same, which means an it has to have rotated. It's no longer vanished. This is like on a plane, for example, where we can just move things flat, but because of the cone. So this is, I can see how like geometry seems to already gets complicated, even this very simple example. So now let's get now into the physics. I'm going to write down the generalization of the Landau. So G is the metric, so square root of G, that's factor. Then we have two terms K and K prime. These are covariant derivatives with respect to Z, Z bar. Since we are in 2D, there's two functions, Z and Z bar. The variations in directions about K and K prime as elasticities. And in this final term, so that's it's like this double. And although it's like very complicated because there's a lot of factors of the geometry. So there's the square root of G, which is complicated, determining. Then we take covariant derivatives. This depends on Christoffels. These and then we use the factors metric. So it's like actually write everything out. But if we make this assumption, if we go deep into ordered limits, so we take the limit where epsilon becomes huge, then Q, then in order to the energy, we're just going to want a phase angle of theta. So Q is like e to the I theta, then just Q, and we put it in your energy algebra, which is those factors of square root of G. Then when we take the absolute value squared, there's no factors of the metric. So the only geometry dependence is through this del phi term. So this expression looks as if it is formulated. There isn't anything, but we're going to pretend as if it's flat.
So grad theta and grad phi are the partial theta by phi. So those are just partial derivatives with respect to
These are partial derivatives, yeah.
Z and Z prime, Z and Z bar.
Yeah, so partial respect to Z, the bar is respect to bar, and the covariant plus are the covariant derivatives. Yeah.
Yeah, so what you said is briefly, but where did the square root of G go?
So I end up cancel form squared. You have to use just ended up those have to contract. So everything just cancels. Yeah. There's some other question.
So I mean, so K and K prime bend and splay. Elasticity essentially, or what are they?
Not exactly. So
Some combinations we do.
Yeah. So I mean, so how do you exactly? What are they?
right, so I guess like first, so not exactly, because we know, because recall that in 2D, let's say just flat, if you want to write down the energy and the Q formalism, there's only one invariant term that we could write down. In the Q, there's like dependence by the equivalent just by integration by parts. So that's one of them. And then the other term is, let's say the K prime term is purely due to the curvature. So we can show that by integration by parts, these two terms and curvature time Q squared, for example.
Okay.
So this is in the spirit of the one.
This is one franc.
In the spirit, because like in the Q language, it's to lowest order in Q and gradients, we can't have the two different.
In 2D, yes.
In 2D.
Because you change the definition of your director so that it's perpendicular, and then you slowly becomes bent.
Exactly. Yeah.
It's just a complex conjugate, right?
Yes.
Yeah.
Yeah, exactly. So that's so if we want to really take that account, then we'd have to add higher order, like nonlinear terms, which one do we give? Okay. Yeah.
So K is basically then essentially this is one franc and K prime is something to do with the geometry of the surface.
Exactly. Yeah.
But is there an easy way for me to see that one of them is purely to the surface, other one is purely to do with the liquid crystal? You know, the ordered field. Can you see that in an easy way? Or because in some sense Z and Z bar don't look to me that different. So you know, or complex conjugate. So it's just so what I'm going to say is that how do I know that it seems that the K prime term goes with the grad Z bar and the K goes with the grad Z. So that means so is there some easy way to see that one of those is to do with the surface?
It's not kind of arbitrary, I guess, because we can convert the K prime thing.
Yeah.
By adding in Gaussian curvature, or we could compute the and get Gaussian. So it just depends on whether.
So I guess
that's arbitrary because. I mean, so that's
experience. That's one, yes.
Thank you.
Yes, one question about the last free energy. So now does it say that you see geometry of the only for higher p-atics, and if you're on a flat surface, any p-atic will look the same in the theory? This is what the last F is saying, because it looks like the P only appears in gradient of the geometric potential.
Exactly. So
if you're on a flat surface, phi is trivial, right?
yes, exactly. It's constant on.
So if you're on a flat surface, any p-atic will look the same.
Exactly.
Just, you know.
Yeah, exactly. Collective logical super. Over this is like del theta minus I del phi, and del phi is kind of like so I actually show that it is actually so if we define U1 gauge fields A, which is like roughly del phi, then if you compute the field strength, then you could show that it's equal to R is easy bar, which is nothing but the Ricci curvature. So it's called the analytical effect. There's a solenoid magnetic field, and because of this magnetic field, then if you send electrons around in different paths, then they pick up phases relative to each other, and that's due to the exactly the same thing happened because of the presence of curvature. It's literally exactly the same. And for the case of a cone, this will correspond to an infinitesimally thin solenoid. Then you have exactly the same thing, but this is just the math analogy with it's exactly the same math. Okay, I alluded a lot, but one of the defects. So top row are the positive charges, the second one are the negative. Plus faster. The reason it's +1 is if you take one of these vectors and it's exactly once. Likewise, I rotate it around the circle, it only rotates by pi. So pi over 2 pi plus 1/2 and that one, so it rotates. And then for the same story, but it rotates.
So for your hex symmetry, you'd expect 1/6 defect or
Yes, exactly. Yeah, so it's just in units of ±1/p. And with the ones we're familiar with is like the +1 and the plus. So you could just generalize it, and for the formalism, it doesn't really change it. So. Okay, now let's use technology. So then let's just sigma m. This is where the data is going to wind around. Suppose there is zm. Then we take the solution for theta, which minimizes energy, and we plug it into the engineering compute. We find. And so the first X term, the sigma and G, this is the defect interaction. For G is the 2D goes like, and no matter like what. Interact with each other. That's all good. And the second term, so we have third times the defect. So we could think about defect and find potential.
You don't need to fix any gauge for this, do you?
No. Just that's like one of the nice things about this coin is that it just boils down to what we're familiar with in electricity. So that's why I was like the potential because it's precise. And it's okay. So biology and collision.
So is this going to be a separate part, or are you going to continue with p-atics? Because if then I want to ask you a question.
I'm going to continue with the p-atics, but allow the geometry to change too.
Okay. Before that, if I am thinking about the way people normally did this, Pelletti, Nelson, or things like that.
Yeah.
Do these kind, if I choose, let's say, a polar order or pneumatic order, choose p equal to particular value, will this just give me the same results as the Pelletti and Nelson, or does this give something extra additional?
I think it's the same results because they did in terms of the grad theta square. So
Yeah,
should get the
that's right. So for your case, this phi is going to be some constant probably, is it?
phi is constant means flat. So if phi is not constant means it's curved geometry.
Curved.
You go to the previous slide and there's a phi and a groups here.
I should point out this was so this effective charge this was pointed out by Vincenzo literally in this.
So do I understand correctly that phi zm encodes the shape of the geometry, the manifold, the 3D manifold?
Yeah, it just encodes the measure like how far away things are. Yeah.
So now you can include phi, time dependent phi, and is that how what you're going to tell us?
Yeah. And it's going to be like general relative. I mean, it is general relativity, but in So now we're going to divert. So a lot of our knowledge comes from studying qualitative phenotypes, like the type of seed, like the colors, etc. Like these are qualitative, and so here's this example that really got me interested. And so there's looking at a fruit fly, I think, and then these are the antenna. If you misexpress one of the media, then you get this instead. So like the end. So if you ask biology, they might be like, yes, we understand this because it's this gene that causes this change. So like that's it, right? Just one gene. But then but if you ask like, hey, this is like this geometry is quantitative, like why instead of that shape? We talk about shape, we talk about like this. So it's very biology knows about geometry. Somehow it encodes it, and then the question is like how the motivation for study morphogenesis. And why study? Okay. So the first question is how can a physicist, by training size, how can physics contribute to is, well, you have a cell and a cell moves, something has to cause it to move forces, so deform, something has to cause it to perform stresses. I'm not going to the answer is physics. We can use physics to bridge very different length scales. So with theories that connect, like for example, this previous example. On this scale of morphological features like antenna. And then somehow there's genes, what you do to gene changes what happens here. And physics is, you can develop theories to bridge these very different lengths. So that's like the one reason. But then we might ask, how can morphogenesis contribute to about physics? And answer is by studying these biological systems, we can be motivated to come up with new systems that we would have not necessarily. Like there's a nice interplay between biological. This is kind of like why I'm interested. This type. Okay, so now we're going to go in depth into Hydra. Explain. So Hydra on the left is like the small freshwater animal. There's a simple body plan, there's a head at the top, at the bottom, and then there's tentacles on the sides. And it's covered by the actin, supercellular actin filaments. They cover like the entire body, they're pretty long and it's pretty continuous. And then if we look more carefully, it's like looks like so there's lines. Since this is the plus one for the mouth, each tentacle arbitrary number. Good and all. So the first observation is that these mouth, foot, and tentacles coincide. But even more surprising observation is not only just namely the sign of the Gaussian curvature is correlated with the sign of the defect. So it means if you look at the tentacles and this, I mean, it's positive Gaussian curvature, and same of the tentacle, like saddle punches, so they have negative Gaussian curvature.
what are we actually looking at in those streaks? Like, what is the subcellular or cellular feature which makes those lines?
Oh, these are like,
How big is the cell on the scale?
well, I don't quite know.
It says
Me,
100
size.
microns, so probably a couple of hundred of these in here.
Yeah, right. I think these are like the fibers they cover many cells and they just go. I think it's in the beginning of the beginning. And thanks.
So in the tentacles, so how many cells will there be in one tentacle, let's say roughly? You think? I mean, just give a ballpark figure. Is it 10? Is it 100? No.
Definitely more than 10, but I don't. So maybe 100, but that could be.
Yeah. Okay.
So will have like length,
Yeah, these are more in depth.
yeah, 100, so
Yeah, I don't know.
30, but
Yeah, the scale was 100 microns.
100 microns. So,
Yes.
so,
With respect to 10, right?
so a tentacle is about sort of 200 microns, something like that, one of the tentacles.
Yeah, it's about 200, maybe a bit more.
Yeah,
200,
200 microns. Okay, so if I think a cell of 10 microns, then basically okay.
20 or 30.
so
Yeah.
we
Okay, so
have
it's-
like these supercellular archangles actually.
Yeah.
Do we know what they actually do mechanically, supercellular archangles? Like, is it just anisotropic, is the contraction going on, or is what's happening mechanically in there?
Good question. So I think it's off my head, but I don't quite
Hmm.
know, but it's pretty, and there has been studies where I think they show that mechanically they do much. Well, because they're myosin optimizing, so it's
So, yeah.
But I guess what you're saying is that in some sense, these are details that you don't care about at the level of your theory because it's our. You know, think of it as a continuum, so therefore you are.
Yeah.
Clearly, yes. Yeah.
So,
yes, at the, which I should know more.
yeah,
At the moment, but then when we actually, if we actually want to make this, so yeah, just treating this as like a model system, but then if we actually want to make very quantitative, then of course we'll get into the details, but we'll see that this will get a lot of features. So
Okay. You can find a similar structure in trans. In trans, meristem is a +1 defect,
oh,
but it's an alignment of microtube. Then the tip is maybe surrounded by the circle. It's here. It's yeah.
Yes, oh,
But
yeah.
then also the two minus one topological defect.
at the base.
When the stem appears, new stem appears, it is +1, but then there are also two minus.
Oh, actually, I didn't know about this plants. I learned something, I know there's a new example.
Which plant? Which plant?
Any plant.
Arabidopsis. I guess Arabidopsis is one of the studies. Yeah.
People study
Arabidopsis.
It's actually
One is the plant fruit fly.
And it's really like this, not like this.
microtube is around.
So it's really like it's really a plus one that
Now this one is the
Yeah.
+1, but with
with a different face.
It's like,
different C means.
yeah, so they're like vortex here.
Yeah.
But here you have two layers.
And,
You have 2 layers.
here the
So there's below there's a crystal pattern. So
you're right. Inside maybe it's perpendicular.
Yes, yes.
Yeah, that's right. And yes, understanding is that so clearly this very we just learned as more universal. So the Riemann chart is it's not just in this system, but it comes up. Yeah, so the goal is also an easy example of this is instead of looking at fingers, we look at our own fingers. So like fingers, we have fingerprints, it's just a bunch of lines. And if you look at the like this part of your finger, it's clearly a +1 defect. It's a common like shape. Right. This looks positive Gaussian. This is positive curve, and then if you look at the base, you can see you probably have 3 lines ish. These are like -1. extended between your fingers. Ultimate example of this idea is look at your hands.
You have to go to the doctor.
No, maybe this works for fingers too. I don't know. I'm not making that. I don't want to think about that.
I mean, there's finally some use for actually reading, people reading hands.
Yeah.
Sorry.
Yeah,
Yeah.
so number of defects related to how long your life is gonna be, you know.
So,
Yeah, you could be, yes.
right, so these observations does suggest that they all work together. So this raises several questions. And also, first of how can the geometry affect the defects? And then what aspects of the dynamics are captured by the intrinsic geometry and reflected in the extrinsic geometry of the surface. So I'll define what I mean later by intrinsic, extrinsic, but the main idea that I hope to into is that the intrinsic geometry is a simple and powerful tool to describe ideal morphogenesis. There's two notions of curvature that are all. One is the intrinsic curvature, extrinsic curvature, such as. Right, so let's go. Examples. Let's say you take this piece of paper. If it's flat, then it has both zero Gaussian curvature and zero mean curvature. However, if we take this and roll it to form a cylinder, this still has zero. But we didn't have to structure it or anything. All we did was just this boundary with that boundary. However, this clearly has non-zero mean curvature. Because if I'm looking at it from outside 3D space, it looks. So in this example, so Gaussian curvature is known as an intrinsic quantity because all you need to define it is just 2D surface. Whereas the mean curvature is an extrinsic quantity because you need to ambience space or 3, so who cares? But you could, but mathematically speaking, maybe we're in ADS or something, and so but technically, formally speaking, extra bit of information. So that's why it's called intrinsic versus extrinsic. So that's why. So like you might say like who cares about this example? But let's say you take it's like you take let's say you're playing with soap bubbles and you have like the rings of the contraption and you put them in this soap film and then you pull them apart. You take them apart from each other and you form this type of shape. So this is a catenoid and it's known as a minimal surface. These objects, they have zero mean curvature everywhere, but non-zero Gaussian curvature. So you might say, so even though this object has non-zero, it has zero mean curvature. So we can't say as the proxy of an object looks curved, it has mean curvature. That's not necessarily the case. So in this example, we have curvature, but non-mean curvature, and this polyconic, we have zero mean curvature. So these are just two. So this different notions and Gaussian. And we there's both, and presumably both are going to be important in this one. But for the purpose of this talk, we're going to focus on geometry, and then we'll see what always there. We can't get rid of it, and if we need to, we'll add on additional information. So that's kind of like the motivation.
I just say we are running pretty slowly, so that's
Okay.
okay.
Okay. So for we decompose it into two parts. The first is just stuff that we have for the right, the same, and the new ingredient G in and so the first term. So we were thinking by spatial. Some of these two, and to start with, we're going to assume defects are in equilibrium, and then we just so we're going to assume it's the axisymmetric dynamics. So the geometry is going to flow such that it minimizes the equation. This is like a plot term. Area, like normal. Eyes, the non-linearities, e to the pi, this looks just like the heat equation. So this looks like the heat equation with sources. Basically, what this means is we have this surface.
And should I see this as a diffusion of the local order or the actual material?
Of the material, this is just
Ah,
this is the
okay,
shape,
sorry, yes,
yeah. Then you have something that this topology is sphere, then after this type of Ritchie flow, it forms a perfect sphere. It's going to evolve. And so, it's going to it's just like having to
The last term there, this A naught minus one.
right.
What's A naught?
Oh, it's like everything like this. I mean, they have lambda. It's like inversely first. It's like lambda, but it's like electron. So if we want to impose,
So
for
if you
example,
go back to the previous slide, with lambda was the
yeah, it's like
the
proportional to lambda,
But okay, so basically it's the square root of g times 2 lambda term. That's where it comes from.
kind of. But you get rid of the square root of g when you do the
Yeah.
Right,
The one of the square root of g, yeah.
exactly.
So it's just that it's basically coming from the lambda term, basically.
Exactly, just so if you want to impose constant area, then you have to choose a specific time dependent form of like such that the total area just. But you can just do whatever you want with it. So for example, maybe it could be used to model additionally, but I just put it there just to. We don't really need that for this discussion, but it's this. So what we're writing here is like the simplest minimal thing you can write down. So the
And so just one last thing, sorry. So the thing, if you want this is a surface covered by surface tension.
right, it's like service.
Yeah. So what happened if you had an energy which was proportional to curvature, like a helpage energy?
All right, so you can do it, but that's how you're ordering gradients.
Yes, yeah.
Because it's like the curvature
Yes,
square,
yeah.
so that's why.
So with this basically break down because then it's no longer no longer heating. You no longer have to solve that Laplace's equation, and so therefore you can't.
Exactly. Yeah.
Yeah. So this works only if you have surface tension, basically.
Yeah. Or even if we didn't have this, even if we didn't have this terminal loss, it's simpler and doesn't work. So
Yeah.
yeah. So as time of services, essentially, this is like the diffusion equation. So then, if you want to find stationary states, we know how to solve this equation in 2D. But the punchline is since just that the defects are, and this tells you. So specifically, the geometry pipe goes describes a cone. Second one shows statics, the charges sorts the potential. We solve that. It's exactly the same here. Defect sorts the geometry. It's exactly the same mathematics. So we just ignore. And because of the skipping over the D. It just falls on the model parameter, so it needs to come to 2. So this is like one prediction that we're.
So what happens if it's too short?
Oh, then our model's not gonna apply. Or we have to add other stuff.
So
Yeah.
probably like curvature.
So,
Or something like curvature, for example.
yeah.
I mean, presumably, I mean,
Because we also have ignoring activity, but ignoring all biological effects. We're ignoring mean curvature. We're ignoring
so and this P, is this for 30 bigger than 4? Is that for P equals to
1.
1?
Yes.
So when you have bigger P, then you get a different limit.
Yeah, but this no matter what P, this is because I want to make this
Yeah,
as
of course, but the other P's are bigger, so therefore
yeah, and of course it depends on 30 degrees. We all know that's
Yeah.
that's easy 30, yeah. So yeah, I mean there's more details in the sketchbook and I'll go over this quickly. So essentially since this is like we could use our intuition equation that you could like a heat equation use some similarity. Like U is like R squared over dt. If you do the transformation, then you could show that for small and large, that's not important. But the point is that we want to model that since these are heights at different times, if you could show that at the maximum orbit of t. And this follows from the diffusion equation type thing. So this is another prediction that we're making, that if there's a topological, if there's a topological defect and is growing from it, it should like square root, which will be another prediction that we're making. And yeah, another example is if you just have, let's say if you have polar order, fixed sphere, and the +1 defects are going to go at the opposite ends. So it's going to be constant Gaussian curvature everywhere except for the north and south poles where there's like a delta function curvature. And another example is if say not uniquely defined, but it's going to be like a saddle or like a monkey saddle, etc. So these are going to be zero Gaussian curvature everywhere except for the origin, which is like so is that answering the going back to the questions? For example, if you want to incorporate mean curvature, you kind of can. It depends. If you assume there's axisymmetric symmetry, then we're going to show that the effect of the mean it forms the limit. More precisely, it's going to so counterintuitively you want what it maybe that it kind of smooths out or lessens the have like a fixed area sphere, and then you want to add a new curvature square, then you want to flatten it so that the bulk of the side is selected, so that's 0. But then the curvature has to go somewhere. It just goes to the tips. So that's kind of like the so to summarize, we set up a formalism of crystals on curved surfaces, and then we applied this to this specific, and we showed how topological defects can source growth. Next steps that many next steps that we're working on is one, we can consider hyperbolic cones, and that means this with instead of positive Gaussian curvature, we mean at the tip like negative Gaussian curvature. So of course in nature there's both positive and negative, and ideally we want to consider both at the same time, but that's much harder. Baby steps. We could introduce activity and then see how biological effects, or we could also consider the effects of finite temperature and these things. So and these are just some of the do and with this I'll conclude and thank you. I'm happy to take it.
What's it?
So the just to understand this energy penalty that you put in as a first approach. So it looks like you can penalize Gaussian curvature even on a closed surface, but somehow this term does not die under sort of Gauss bonnet. You know, if you put in Gaussian curvature directly, it sort of doesn't play a role on the. So what's happening? How can you?
Oh yeah, that's a good. So then
Yeah. I mean, if it's easier to do this afterwards because it's lengthy, then we can also separate.
I can say a comment and then. I'm just add. If this is like. What will we do instead?
This is the corresponding to the.
That's a kind of.
Right.
But I don't.
Higher order in curvature. Yeah, it's
Yeah, I mean,
length scales, I guess.
Yeah, the next.
Okay.
Thank you. Yeah.
I have two questions, but maybe they are related. So now with your formalism, because you told like it just brought my imagination. I have a sphere, I can elongate it, but can it be done that if you just give a profile on your surface and your formalism can tell what should be the topological defects developed?
Yeah, maybe, yeah.
And
Yeah.
another thing is with activity, do you mean motility? Because
For
activity
yeah.
for me is also growth. The growth you have is already some sort of activity.
Yeah, bacteria, just bacteria, I mean like biological activity, so it could mean, yeah, just anything that any like non-equilibrium.
Because for me already what you show is sort of activity.
Well, in some sense, you could say that what he's telling you is that it's finding the optimal surface. So it's which is the df when df by d defines 0, that's the optimal surface. So this is kind of a relaxation towards that optimal surface. So, but I guess you can imagine that you're putting some energy, which then means that it doesn't ever get an optimal surface. It's constantly there.
Like it could maybe there's like some flow, like maybe some osmosis causing to flow, or there could be. But maybe there's other sources, like maybe there's some chemicals and there's gradients and there's. Yeah.
I think I more like a chicken and egg question or a comment, right? So how far is the, are these topological effects actually effects important for development of shape, or you just develop a shape and then since you have a positive Gaussian curvature, you happen to have a topological effect? Maybe, I have a topological effect on the tip of my finger, but I don't think this is responsible for my finger looking the way it does, right? See what I mean, right?
Yeah, that's good. So my understanding is at least looking from the Hydra experience, seems to be the defects came slightly before the growth, but I could be completely wrong about whether. But it's a good question. Yeah, I guess in here where I just assumed there were defects present, so I didn't say how they develop. I just said assume that they're there, and then if they're there, this is what's going to happen here. But it's a good question.
For example, in the show experiments, right, with the MDCK cells, I mean, they made a kind of quite a bit of splash about that these topological defects have extrude the cell, but there is also possibility that cell died, and because of the stress distribution, you just form a topological defect, right?
Exactly. Yeah. So that's it. That's my answer. I'm just going with what they.
So to follow up on that for the Hydra is like, is there some known morphogen patterning or something like that, which decides how many tentacles this thing gets? Like, is it equivalent of Fox genes or something like that?
Right, so I think the number of tentacles isn't fixed. I think if you start it, then there's fewer tentacles. So there's stuff like that. So it's not. Yeah, that's my rough understanding. Is it's not always 3 or whatever it is. But I could be wrong. But I think that's a good question. If we could actually predict the number of tentacles or how far apart they're spaced or something.
But if it's not free pattern, that actually would support the physics approach here.
Yeah.
So there's certainly wind signaling involved. Because you can stain and fix animals for wind and you see it always at these places. Unfortunately, as far as I know, there's no marker that would allow you to dynamically follow the expression of wind. So morphogens are definitely involved in some way.
Yes.
Any final question?
Well, just a general comment. I mean, Hydra is well known, of course, for its being regenerative properties, the fact that you cut it and then it grows another head. So, I mean, is there anything? Is that purely? One thing about that is purely something that's going to be active, or do you have something to say about that? With the
What do we say about heads growing?
about basically about the ability of this thing to to regenerate if you cut it into pieces. Is there? I'm just not asking. That's what I know about Hydra, and so I want to know. Can you say anything about that, or is that essentially for you something that comes further down the road, if you want?
Presumably there's a lot of I mean, we could say that this would, if there's somehow defects formed, then it could cause the general shape formation, but actually forming a head with all its function, that's I don't think how the generation works. That's presumably there's a lot of
So, any last question from Notani? Talk about that. Anyone? Okay, then let's thank Farzan again.